I've worked through what different graphs of the kinematic functions look like, and now I want to work through an example. That's what this video is going to be, an example of how to make and use these graphs. So I've started out by giving a graph of position versus time, that's this top one, and some questions to answer. I want to construct the corresponding velocity versus time graph, and I've already given a blank axis for that, set of axes for that. I want to do the instantaneous velocity at t equals 20 seconds. I want to find the average velocity over the first 20 seconds, the average velocity from 10 to 20 seconds, and then I'm going to construct the corresponding acceleration versus time graph. Won't be awful. So first, constructing the velocity versus time graph. For the first 12, 14, 15 seconds, I am getting a constant speed. I'm moving at some speed. I'm getting 30 meters. I'm doing that in 15 seconds. So 30 meters over 15 seconds means I have a speed of 2 meters per second. So for the first little while, for the first 15 seconds, I'm going to get a speed of 2 meters per second. And it's a flat speed, not speeding up or slowing down. From there until I get to t equals 18 seconds, I'm at rest. So right here, I am at rest. It makes sense that I've got to jump because I have this cusp right here. So I've got to jump in this graph. From there, over the course of the next 4 seconds, I'm going to move 10 meters back. 10 meters in 4 seconds is 5 meters in 2 seconds, is 2.5 meters per second. I'm moving in the backwards direction. So if that's -2, -3, I'm moving at -2.5 meters per second. I'm going to do that for 4 seconds. After that, now I've got an interesting thing. This is some kind of a parabola. So if I've got a parabola in my x versus t graph, I know I'm going to get a diagonal line in my v versus t graph. I start off at the same speed. This continues. So I start off at that speed, and then at the end at 30 seconds, I've gotten to a speed of 0. That would be my turnaround point. So I'm going to connect just like that. I don't have a cusp here. There's no corner. So I don't have a jump here. But that's my velocity versus time graph. Next, I want to find the instantaneous velocity at t equals 20 seconds. An instantaneous velocity tells me that I want to be looking at my v versus t graph. So at t equals 20 seconds, I look at my v versus t graph. I am right here. That's going to be -2.5 meters per second. Next one, I want to find the average velocity over the first 20 seconds. Average velocity tells me I want to look at my x versus t graph. I'm going up one level. So over the first 20 seconds means I'm starting from t equals 0. I'm going to t equals 20, which is right here, and I'm connecting those with a straight line. I am effectively finding the slope of that straight line. So my average velocity for those first 20 seconds, I'm going to say v average is x at t equals 20 seconds minus x at t equals 0 seconds over 20 seconds minus 0 seconds. At 20 seconds, my position is 25 meters. At 0 seconds, my position is 0 meters. (25) divided by 20 is 1.25. meters per second. Next, I want to find my average velocity from t equals 10 seconds to t equals 20 seconds. I'm going to change color because this is going to start to be a very busy picture otherwise. I'm looking for an average, so I again want to look at my x versus t graph. From 10 seconds, I'm here, to 20 seconds, I'm there. So I want to connect these 2 points with a straight line. I'm going to say V average is going to be x at t equals 20 seconds minus x at t equals 10 seconds divided by 20 seconds minus 10 seconds equals x at 20 seconds is still 25 meters. X at 10 seconds, I'm grabbing right here, that's 20 meters. Divided by 20 minus 10, that's 10 seconds. I get 5 over 10 is a half a meter per second. And then the last one, constructing the corresponding acceleration versus time graph. So I'm going to have, again, my same axes. Time and acceleration. And I'm going to start doing some of these. For the first 15 seconds, I've got a flat line. If I've got a slope of 0 here, that means I'm going to get an acceleration also of 0. The other way to think about that, my velocity or my speed, whichever way you want to think of that, is not changing. It's 2 meters per second the whole way. If my acceleration is the rate of change of velocity, it's not changing, so that's it. Then from 15 to 18 seconds, I've got a flat line again. Okay, from 18 to 22 seconds, I've got a flat line again. And then the last part, from 22 seconds to 30 seconds, now I've got something. I'm going from negative 2.5, so I'm going from negative 2.5 meters per second up to a final speed of 0. Acceleration is v final minus v initial all over t, and it's taking me 8 seconds to do this. So I'm saying v final minus v initial all over t. When I calculate this, I get 0.33125. So maybe I've even got room to say 0.1, 0.2, 0.3, 0.4. I have an acceleration here. The slope of this line is constant, and it's 0.3125 meters per second squared. The slope of that line is constant, so I'm going to get a constant acceleration of 0.3125 is something like here. And that's going to carry me through to the end. Being completely correct here would say I've got this constant positive velocity, then a 0 velocity, so I slowed down in between, but I did it in no time. So maybe you would see a spike downward, and then same thing here. Maybe you would see a spike downward if you were looking at this in a book. We're not. Maybe here you would see that spike upward. I guess it would really even look something like that. These spikes, we don't generally care about we're looking for what the segments are in between. But if you were going through a textbook, you might come across those. But that's it. That's an example of how I can use these graphs and how I can create more of them. And there is a velocity graph, or a position graph up here, corresponding velocity, corresponding acceleration.